Welcome to the Explainer. If you're a computer science student trying to finally wrap your head around abstract data types before your next big exam, you are in exactly the right place. Today, we're taking a structured, visual journey through the core concepts that literally form the backbone of modern software engineering.
Here's our game plan for today. First, we'll be defining abstract data types, then comparing ADTs versus data structures. After that, we'll look at a flight reservation system, starting with option 1 and then looking at a much better option 2. Finally, we'll wrap up with a summary and your key takeaways. We're going to move sequentially, starting from pure abstract theory and then bringing it straight down to concrete code implementations so you have hard proof as to why these programming patterns matter so much.
All right, part 1, defining abstract data types. Let's dive right in. To build really great software, we first have to understand the foundational theory of what actually makes a data type abstract in the first place.
I want you to mentally highlight this definition for your exams. Encapsulation. An abstract data type, or ADT, is a definition of a data type solely in terms of its data items and the operations performed on them. The real magic here is encapsulation. It's the strict separation of logical properties from implementation details. In really simple terms, it effectively hides all the messy under-the-hood details from the user who's actually interacting with it.
Visually, it acts like a literal boundary. Take a look at the outer ring labeled interface. Notice how it physically wraps around and completely hides the inner core, the implementation, from the user up at the top. The user only ever interacts with the interface, the operations, and they never need to know what kind of complex code is running inside that blue inner circle.
Which brings us to the golden rule of ADTs. What, not how, is the focus. If you literally only remember one thing from this explainer, make it this. We care entirely about what the data type does, what data it holds, and what operations it can perform. We do not care at all about how it's built under the hood.
To put this into perspective, think about the ADTs you already use every single day. Take whole numbers or integers in programming. You perform arithmetic operations like addition or subtraction on them all the time. You know exactly what a plus sign does, but you definitely don't need to know how your computer's processor implements binary addition just to use it. Another great example, and one we'll actually be coding out shortly, is a flight reservation system. The data is just a list of seats, and the abstract operations are finding an empty seat, reserving one, or canceling a seat assignment.
Moving on to part 2, ADTs versus data structures. Let's shift our focus from pure abstract theory to how this actually lives in physical memory.
So, how do we make an ADT functional in the real world? Well, we have to implement it. This implementation boils down to two main things: storage structures to hold our data items and algorithms to execute our basic operations. We pull off this separation of the data type from its implementation by utilizing either the built-in language constructs provided by our programming language or by building our own user-defined constructs.
Now, before we look at any actual code, let's clear up a super common misconception about where a program's data physically lives. You might hear data structure and file structure and assume they're interchangeable. They absolutely aren't. A data structure refers to the organization of data in main memory, like your RAM. It is the physical implementation of an ADT where operations are handled by subroutines. A file structure, on the other hand, is the organization of data on peripheral storage, like your hard drive or SSD. Keep that distinction crystal clear in your notes.
Let's trace how this logic maps straight into physical memory. Following the flow here, at the top, we have our abstract data type, made up of its logical data items and abstract operations. That maps directly down into the data structure. The logical data form becomes physical storage space, and those abstract operations become physical subroutines. It is a perfect one-to-one translation from concept to code.
Which brings us to part 3, flight reservation, option 1. This brilliantly illustrates everything we've talked about. Let's look at a concrete, exam-relevant code example for an airplane flight that has exactly 10 seats to be assigned.
Picture this scenario. We have a flight with 10 seats. Our required ADT operations are simple: list the available seats and reserve a seat. But how do we actually store and access this data? Well, let's start with a pretty naive implementation method: storing the state of our airplane using 10 separate individual variables.
Take a look at this pseudocode. It's pretty rough. To list the available seats, we have to write out, if seat 1 is empty, display 1. If seat 2 is empty, display 2, all the way down to seat 10. And look at reserving a seat.
We have to set a done Boolean defaults, check if seat 1 is what the user wants, ask for confirmation, change the variable to an X, and set done to true. Then we have to copy-paste that entire block of logic for seat 2, making sure to check if it's the requested seat and ensuring done is still false. Can you imagine the sheer tediousness and edge case nightmares of writing this out for a commercial airliner with 300 seats? It's just a massive wall of nested if statements.
That brings us to part 4, flight reservation option 2. Clearly, that first approach is not going to scale. So let's shift gears to a much more elegant solution. How can we implement those exact same abstract operations, but with a far better underlying data structure? Here's our second implementation option. Instead of using 10 individual disconnected variables, we're going to use a single array of variables to handle those same 10 airplane seats.
Just look at how drastically this array syntax cleans up our logic. To list the available seats now, we just use a simple zero-indexed for loop. For a number ranging from 0 to max seats -1, if the seat at index number is empty, display the number. That's the whole thing. 2 lines of code just replace 10 isolated if statements. And reserving a seat, we just read the requested number, check if the seat array at that direct index is empty, and if so, set it to X. Otherwise, display that it's occupied. This elegant solution completely eliminates the 10-variable nightmare and all that messy Boolean tracking we saw in option 1.
All right, part 5, summary and key takeaways. We've covered a ton of ground, so let's quickly recap the fundamental rules and programming patterns you absolutely must remember for your exams.
Drawing from everything we just looked at, here are your core rules. An abstract data type always consists of a collection of data items along with the basic operations that must be performed on them. In our flight example, the data was the list of seats, and the operations were listing the available seats and reserving a seat. The absolute most important takeaway here is this. Regardless of whether you implemented that data using 10 clunky variables or one sleek array, the ADT's logical definition, its interface, never changed at all.
I want to leave you with this one thought on the true power of encapsulation. If you design your software correctly using abstract data types and you completely rewrite how your data is stored in memory tomorrow, say swapping from variables to an array or even an array to a massive database, will the rest of your program even notice? The answer should be a resounding no. And that, my friends, is the secret to scalable, modular software engineering. Thank you so much for joining me on this explainer, and best of luck with your upcoming assignments.